Hello everyone, and welcome to the final video in my series where I'll discuss the progression of my Arduino Uno security light design project. In this final video, I'll be going through the entire design process from start to finish, and I'll end off with a full testing demonstration of the finished product that I ended up creating. For those that have not seen my previous videos, I was tasked with creating a security light system using an Arduino Uno R3 and various sensors, and it had to have test input and battery charge testing capabilities. At the beginning of the project, the first considerations for the components involved in the design were made. The specifications required that the security light would remain off during the daytime and in high light conditions. It would then be active and turn on when motion is detected in the nighttime or during low light conditions. Additionally, I needed to find a way to accommodate test input, which would allow the user to test the lights. And I also had to display the battery charge level to find a way to get this information to the user. The implementation for this that seemed to make the most sense involved the use of a motion or PIR sensor, a light-dependent resistor to check the lighting conditions, and then I'd use a push button to allow the user to test the lights, as well as the charge level of the battery, which would be displayed via an LCD screen. The button, as well as the appropriate motion and light signals, would then send a high signal from the Arduino to one side of a relay, with the other side connected to the lights. Once I had determined the necessary components for my design, I was able to come up with the first concept for my circuit diagram. This first circuit underwent many changes as I became more familiar with my sensors and power requirements, but many of the connections remained the same until the end. As you can see here, to measure my battery charge level, a simple voltage divider for my battery was used. That way I could send a safe, low voltage corresponding to my battery voltage level to my analog input pins, which could then be translated to the real battery voltage via voltage divider rule. On the right side of my Arduino, I have my LCD screen interfacing with my digital pins in 4-bit mode, as well as my other sensors which are powered and grounded. Some of the main changes that I had to make involved the battery, as I wanted to use a 9 volt instead of a 12 volt to make the device more compact. Moreover, the transistor and several resistors shown here were removed, as the sensors and relay modules I used had such components already built in. Lastly, I had originally intended to have my light bulb supplied by 120 volts AC, but it was not only safer but simpler to use 120 volts AC to 9 volt DC adapter to supply my lights on the other side of the relay. I also decided to try and get the most out of my 9 volt battery and implement low power mode via interrupts to conserve energy during the daytime when the system is typically off. To do this, I had to send my motion sensor signals to digital pin 2 on the Arduino. Once I had a theoretical circuit ready and sketched out, the next step was naturally to test it. However, some preliminary testing in the form of simulation is always good practice. Using the open source Tinkercad software, I was able to make a circuit closely resembling my own, which successfully replicated the functionality that I was looking for. As you can see here, motion detected in the dark successfully flips the relay and turns on our light bulb. However, when I switch this such that the LDR is reading high light levels instead, when we detect motion, the light remains off this time. In this simulation, I was also able to set up the test input feature, where at the push of a button, you can test the light bulbs and check on the charge of the battery, which is displayed on the LCD screen. Obviously, in this simulation, I'm using a supply instead of a battery, and the reading is off compared to its expected real-life counterparts. Tinkercad also offers a basic CAD modeling feature for 3D parts. Early on in the design process, I was able to use this to get an idea of my box size and dimensions, as well as play around with the organization of my components both inside and the lights and sensors protruding from the box. Although my final finished product, which we'll see shortly, doesn't end up looking quite the same, it's very close and allowed me to visualize what the finished product could look like. My finished product ends up looking slimmer and more compact, and I opted for the motion sensor placement on top of the box to detect motion from multiple angles to ensure better security. After this, I was ready to build my first prototype on a breadboard, which would allow me to easily test my circuit, obtain my power characteristics, and troubleshoot the circuit if need be. As you can see here in this video, I managed to successfully get this working. In the light, the circuit worked as expected, and then by covering the light-dependent resistor, my motion behind the camera triggers the motion sensor and flips the relay, turning the lights on. As you saw here, I also measured how much current my Arduino is pulling in its different operating modes to understand the power consumption compared to what I had expected, which was lower than expected by about a factor of 10 with the help of low power mode. As you can see here, I'm also able to test the input and check the battery charge level at the press of a button. Again, as planned, you can see my sensors here interface with my digital pins, LCD screen, and one side of my relay, which connects to my 120 volts AC to 9 volts DC adapter on the other side to power my light. So now let's break down the code that I used for this and see how it all comes together. So we start here by including the liquid crystal library for the LCD display, as well as the low power library for reducing power consumptions. Next, we initialize the LCD with the interface pins. The liquid crystal object LCD is created with the pins for RS, E, D4, D5, D6, and D7, as we're using 4-bit mode. We then define the pins for the relay, the PIR sensor, button, photoresistor, battery level measurement, and the LCD backlight. These are constants set to the respective Arduino pin numbers. Following this, a light threshold value is defined to determine when it's dark. Additionally, resistor values for a voltage divider used in battery level measurement are specified. As mentioned, for power saving mode, two Boolean variables, motion detected and button pressed, are declared here. These will be modified by the interrupt service routines to indicate when motion is detected or when the button is pressed. In the setup function, we then initialize the LCD and set the initial state of the backlight and relay to off. We also configure the PIR sensor and button pins as inputs with pull-up resistors. Finally, we attach interrupt handlers for the button and PIR sensor, which will be triggered on falling and rising edges. Next up, in the main loop, the Arduino enters a low power mode until an interrupt occurs. That way, if motion is detected and it's dark, the relay is turned on for 5 seconds and then turned off. If the button is pressed, a separate function handles the button press. Moving on to the interrupt handles, the pin interrupt handler sets the motion detected flag to true, and the button interrupt handler sets the button press flag to true. We then need to check darkness, and so the isDark function checks if the light level read from the photoresistor is above the threshold, indicating darkness. Finally, the handle button press function turns on the LCD and the backlight, which displays the battery charge level and turns on the relay. It then waits for the button to be released before turning everything off again. As I went on to test this further, I did encounter some issues early on with my light-dependent resistor. So when I was first working with my LDR and my prototype setup, I was slightly puzzled as to when my sensor was telling my system was either bright or dark. Upon further inspection and some research, I could recognize that this particular LDR is configured such that in bright light, the LDR's resistance is low, so the voltage at the node, and hence at my analog pin, is closer to ground. Conversely, in darkness, the LDR's resistance is high, and so the voltage at the node and at my analog pin is closer to 5 volts. due to the voltage divider formed by the LDR and the 10K resistor included in the module. So after coming to this realization and playing around with my prototype quite a bit, I recognized that the LDR threshold that made the most sense and seemed to consistently flip the relay when appropriate was at a value of about 500, which remained as so, and was included in my final product. I didn't encounter any issues with my PIR sensor, but I did make some adjustments during later testing. So coming out of the box, the PIR sensor seemed to only pick up on motion from the minimum of its range at about 3 meters. For maximum security purposes, I reasoned that the system would benefit from motion detection at its maximum range of about 7 meters. And I adjusted this by turning the sensitivity adjustment potentiometer clockwise. After these fine-tuning measures, I was able to transfer my circuit onto a soldering board to secure the wiring for a permanent fixture that would rest in my finished product. Then I was ready to build my product housing, which would enclose my circuit. I did this by sourcing a slim 10 centimeter by 10 centimeter by 5 centimeter box and customizing it for my sensor placement, and then organizing my wiring inside of the box. Before enclosing the box, I went through some final testing to ensure my circuit was still intact, and I cleaned up the soldering ends on my board, as shown here, to avoid any connections falling out or shorting when fixing my components inside of my product housing. My soldering boards and Arduino were either secured with hardware or double-sided Velcro inside the box, such that nothing slides around as the housing is moved. All sensors protruding through the exterior of the box were also fixed in place. Finally, after getting everything closed up, my product was finished. As you can see, I modified the housing and heat shrunk any of the wiring associated with sensors that came out of the box. This was to enhance its lifespan and protect the wires, protect the consumer. As mentioned, my LCD and button are on the back of the box, and I also have my motion sensor placed on top of the box alongside my LDR. With the final product done, all that was left was to verify it worked as expected. As you can see in this demo, with the LDR sensor exposed to the light, motion doesn't flip the lights on. However, when I cover that sensor up to simulate darkness, my motion begins tripping the relay and turning the lights on. We also can't forget the other specification. As you can see here, with the press of a button, the lights can be tested, and the charge level of the battery is also displayed to the consumer on the LCD screen. To market the product, I went through the process of creating a brochure that would communicate the product to potential customers. Although a security light like this is not the first of its kind, its simple yet effective design could interest anyone interested in increasing their home security measures. This brochure mentions the specifications, dimensions, and features of the final product. If I were to continue working on this product, future iterations would possibly try to get even more out of the battery and possibly have the entire system be battery powered. I'd also go about making the product completely weatherproof with the necessary cable glands and materials. However, in its current state, the product can be considered a success. Thanks for watching.